See, uh, in the previous classes we discussed about classification of metals, insulators, dielectric material, semiconductors and superconductors. Then we defined about what is resistivity and what is conductivity. Okay. Then we discussed about classification, the values for metals, insulators and semiconductors. Okay. Then the classification of semiconductors, we have intrinsic and extrinsic. Intrinsic means silicon and germanium. Extrinsic means p-type and n-type. That is, intrinsic means pure, extrinsic means impure. Then we discussed about core electrons and valence electrons. Core electrons means the electrons which are close to the nucleus, and valence electrons means electrons which are in the outermost orbitals of an atom. Next one is valence band. The band formed due to the valence electrons is known as valence band, and the band formed due to the next higher band of valence band is conduction band. Means if it is for one atom, we say core electron and valence electron. If it is for thousands or millions of atoms, then we cannot speak in the term to be used is band. Okay, valence band and conduction band. Valence band is the band formed due to the valence electrons is valence band. The next higher band of valence band is conduction band. What is forbidden band? The gap between valence band and conduction. The gap between valence band and conduction band is forbidden band. Okay. Next we have see here for energy level diagram. So for energy level diagram, this is for the conductors, where conduction band and valence band they completely overlap. Means no energy is required for the electron to jump from valence band to conduction band. Just you apply the potential difference, electron starts flowing, because there is no energy required to move the electron from valence band to conduction, because they overlap. See, they overlap each other. Conduction band and valence band, they overlap each other. Whereas in semiconductors, valence band and the gap between the valence band and conduction band is less than 3 electron volt. Now coming to the insulators, the gap between valence band and conduction band is how much? More than 3 electron volt. That is insulators. Is that clear? So that is about the energy band. Next one is we have n-type and p-type semiconductor. So how much energy is required? In germanium it is 0.72 electron volt, and for silicon n-type semiconductor is how it is formed, that I will tell you. Okay, n-type semiconductor means when you join, where is that? Yeah, here it is n-type semiconductor. So before going to n-type semiconductor, there is a classification. We have 3A group element, 4A group element and 5A group element. 3A group element is also known as 13th group, 4A group 14th group and 5A group is 15th group. So boron, aluminium, gallium, indium, thallium. That means it has 3 electrons in the outermost shell. See, 4th group and 5th group, these are the elements. This boron, carbon and nitrogen, these are gases. And thallium, lead and bismuth, they are a radioactive element. So we don't take the first one element and the last element. We only take these middle elements, 3 elements in each group, for the formation of n-type and p-type semiconductor. So this 3rd A group element is also known as trivalent, 4th A group element is known as tetravalent, 5th A group element is known as pentavalent, because this has 3 electrons in the outermost shell, 4 electrons and 5 electrons in the outermost shell, and which are ready to participate in the chemical reaction. Next one is n-type semiconductor. In n-type semiconductor, now the next term is doping. Addition of impurity to a pure semiconductor is said to be doping. How much is the doping? 1:10,000, means 1 impurity to 10 to the power of 18 atoms. So that such is that ratio. In that ratio, we mix the impurity. Like if when you're preparing the dough, you might have seen like we put a little pinch of salt in that one. Pinch of salt in the dough. So that much, very very little is the impurity, right? So the same way. Next one is in n-type semiconductor. Like suppose this is a pentavalent and all the B's are tetravalent. So one excess electron is available for every combination. So that is the reason number of electrons are much greater than number of holes. Coming to p-type semiconductor, X is a trivalent and for every combination we have one hole. So number of holes are greater than number of electrons. Next is what? Hole is what? Vacancy part of electron is said to be hole. Understood? Next one. So the next one here, is it clear? Is this clear, sir?
Yes, sir.
Yeah. Now for germanium, are you there, Sayam?
Yes, sir.
Yeah, okay. Now for germanium, the gap between the valence band and conduction band, how much energy is required? So you require 0.72 electron volt for germanium. For silicon it is 1.1 electron volt. Now you might ask, what is this value then, sir? Actually this value is for the Fermi level. Means, like suppose there is a dotted line here. This dotted line is the difference between the donor energy level and the band. Here acceptor energy level and the band, that energy is here 0.01 for germanium and 0.05 for silicon. Got it? And this is the energy gap for germanium and silicon. Now, so we have to maintain the neutrality. How they maintain the neutrality? Like here, this is shown here in the diagram. For this is for N type and this is for the P type. Ni is for the intrinsic. Generally, for the pure metal, we say intrinsic, and Ne number of electrons and Nh for number of holes. Now here in P type semiconductor, number of holes is much greater than number of electrons. Okay, if you multiply it, it is greater than, that is Ni square. Okay. Now energy band. So see here, this is valence band, conduction, energy of the valence band, energy of the conduction band, and the gap is energy gap. The donor energy level is very close to the conduction band in N type, and in P type the acceptor energy level is very close to the valence band, and here it has excess number of holes and here it has excess number of electrons. That is the difference. Now what next concept is p-n junction diode. What is a p-n junction diode? When a p type substrate and n type substrate are brought together, then a p-n junction diode is formed. Generally at the junction all the minority charge carriers are available. I give an example, like suppose if one boy is made to sit in a girl's classroom, or one girl is made to sit in a boy's classroom, it is not comfortable. They are not comfortable. They just want to move away. The same way, minority charge carriers are ready to move away. So when you apply certain potential difference, they start the electrons and the charge carrier starts flowing. So here we have in N type we have electron diffusion, and here we have electron drift. Here also same we have depletion region. This is a hole drift and hole diffusion. Now, so here depletion region, next is potential depletion region. This region is said to be depletion region. The barrier is said to be potential barrier. And here we have recombination of electrons. That electron hole recombination takes place. Okay. Now, what is depletion? Depletion region means a narrow region where the junction is depleted in mobile charge carrier. Okay. A very narrow region. This region is said to be depletion region, also known as space charge region, or the potential difference developed across that one. Like this here, the small potential difference is developed here. So this potential difference is said to be potential barrier. So due to accumulation of charges near the junction, electric field is established. This gives rise to electric potential. Understood? So this is a definition of barrier potential. So small potential is there here. So how much it is? It is for germanium it is 0.3 electron volt, and for silicon it is 0.72. That was energy gap. Once again, what we studied here before, this is energy gap, the gap between valence band and conduction band. This is the gap. But what is this? This much is the potential. When you bring a p type and n type substrate, for germanium it will be this much potential is developed, and for silicon this much potential is developed. Now here this is the code I studied, that I have explained. That is not required. Okay. Now forward bias. What is forward bias? Forward bias means when a p type substrate is connected to positive and n type substrate is connected to negative, then we say the diode is forward biased. And here if n type p type is connected to negative terminal and n is connected to positive terminal, then that is said to be a reverse bias. So we have forward bias and we have reverse bias. P is connected to positive and N is connected to negative of a battery. So that is forward bias. Here the forward resistance, here as you increase the voltage, current also increases, and the current is measured in milliamperes, and the resistance is only 10 ohms to 30 ohms. Whereas in reverse bias, P is connected to negative and N is connected to positive. So that is said to be a reverse bias. Now, so as V increases, current also increases. As voltage increases, current also increases. So you have seen this is a forward resistance, okay, and the range of the voltage is also given. You have to increase like from 0. Like 0 to 1 voltage with a difference of 0.1. We cannot go more than 1 voltage, otherwise the junction will spoil and the diode will burn. Okay, so there are some restrictions for forward bias. The voltage applied should be not beyond 1 voltage, and for reverse bias it should not be beyond 10 voltage. So as V increases, current also increases, and there is a electron hole recombination. Okay, and reverse saturation current or leakage current takes place. Okay, so that happens in the reverse voltage. The voltage at which the diode breaks is known as breakdown voltage. Okay, so next, so that was about the forward bias and reverse bias. 1 second. Okay, so we were discussing about forward bias and reverse bias. Forward bias means if P is connected to positive, suppose if the once again see here, if the P is connected to, this is P and this is N, if P is connected to positive and N is connected to negative, then we say it is in forward bias. Okay, this is forward bias. Now what is reverse bias? If P is connected to, this is P and N, this P is connected to negative and N is connected to positive, then we say it is reverse bias. Okay, we say it is reverse bias. So we have forward bias and we have reverse bias. Okay, forward and reverse bias. Next, now you know the symbol also. The symbol is in this way. The diode symbol is in this way. So we say positive. This is positive and this is negative of the diode. So now we have to study about the VA characteristics of a junction diode. We'll study about the So if you look at the diagram, okay, now we will study about the VA characteristics. This is there in your practical also. VA characteristics of a junction diode. Did you do this experiment of a diode? VA characteristic of a diode. Did you solve this one? Did you do this experiment in your lab? No reply. Did you do this experiment in the lab?
Yes, sir.
Yeah. Suppose this is a diode and see first I am taking a variable power supply. So where you can increase and decrease the supply. Okay. So this is a, now here it is a milliampere. This is positive, negative. This is milliampere to measure the current, and this is a voltmeter. Okay. This is a voltmeter. This is milliammeter and this is voltmeter, and this is P and this is A. Okay, this is P and this is a switch. Switch is K I am writing here. And this is variable power supply. You increase the voltage. How much you increase the voltage? See voltage how I am increasing 0, 0.1 to 1. What is the meaning of this? Means 0, we are starting from 0 ending at 1 and with a difference of 0.1. Means it should be how much? 0 to 1, 0, 0.1, 0.2, 0.3. Okay, so like it will be in this way. See serial number we write here, voltage in volts, potential difference, this is potential difference in volts, and current in milliamperes. So what will happen when you do this experiment? 1, 2, 3, 4, just okay, suppose if I am doing this experiment, how will be these readings? Just I want to show you. 10, so 11. Okay, starting from 0, 0, 1, 0, 0.1, 0.2, 0.3, 0.4, 5, 6, 7, 8, 9 and 1. Then here it will be 0, 0, 0, 0, 0, maybe 1, then 2, then something like 7, then 9, something like 10, and then 11, something like this it is. Okay, when you do this experiment. Okay, practically when we are doing this experiment in the lab, maybe these are the readings what I feel. Now the same experiment, when you this is for the forward bias, and now I am doing this experiment for the reverse bias. In the reverse bias, what I do, the diode is kept in this way, positive and negative, and here this is the negative supply, and now here this is voltmeter, this is P, this is N, this is negative, this is positive, should be connected in other way. Yeah. So this is a variable battery, and here this is a microammeter, and this is a switch. Okay, I'll just keep a switch here. The current is in here, it is 10 to the power of minus 3. Here the current is 10 to the power of minus 6. Here that current is, why the current is flowing? Because of the minority charge carriers, because of the electron hole recombinations, because of the minority charge carriers. Keep that in the mind. That also is known as leakage current. Here, how will be the voltage? The voltage should be in this way, 0 with a difference of 1, it should be up to 10. Understood now? 0, starting is 0, ending is 10 with a difference of 1. So how will be the current? So here see the potential difference in volts, and current is in microamperes. So if you see 0, 1, 2, 3, we might have done this experiment. So what all will be the Viva questions also I am going to discuss now itself. Now, so how is the difference? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This is 0, 1, 2, 2, 3, 3, 3, 4. Like very small current, okay. Almost all same. Okay, such is the very small current flows through this one. That also is known as due to the breakdown voltage or Zener breakdown. At a particular voltage, no more current flows. Means the current remains constant. After that, it will break. Okay, if you apply more voltage, then it will break. We'll draw the VI characteristic. Okay, maybe in your lab did you get this type of readings, Zayan and Sayam, when you are
We
doing
don't
this?
have reverse bias.
Yes, sir.
Yeah, something like this. Not exactly the same, because it will vary from one diode to another diode. That also. Okay, if I draw the VI characteristic of a diode now, if I draw the VI characteristic of a diode, how it will be? See here. See, I'm taking a drawing this diode. So VI characteristic. One second. Now it is something like this, and for reverse bias it is something like this, and suddenly it starts increasing. Here it will become like 1 to something like 10. Okay, just I'll write that. It will become 10, 12, then something like current remains constant. It will break down from there to a 13, 14, 15, something like this. Okay, or something it will be 40, 50 also. So if you when we draw the VI characteristic of a diode, so this is volts and current, it is in milliamperes. Here also this is here this voltage is said to be breakdown voltage, VBR we are writing, and the current here it is in microamperes. So if you look at this one, how is this class breaking? It is 0.2, 0.4, 0.6, 0.8, and 1. So 0.2, 0.4, 0.6, 0.8, then 1. And here it is 20, 40, 60, 80, and then 100. 60, 40, 20, and 0. And here it is 20, 40, 60, 80, and 100. Here also it is 10, 20, 30, 40, like this it gives one way. Clear? So that is how the This is about a VI characteristic. Okay, this is about small current is flowing leakage. This voltage, this particular voltage is said to be the breakdown voltage. When you increase little voltage, then the more current starts flowing. So, this threshold voltage, the voltage at which the current starts flowing through the diode, the voltage at which the current starts flowing is known as knee voltage or threshold voltage. Knee voltage. So I'll write that one here. The forward, the definition for that, the forward voltage required, the forward voltage required to get the junction, in conduction mode, is called knee voltage or threshold voltage. Knee voltage or threshold voltage. One second. Yeah, knee voltage or the voltage here. Okay, knee voltage or threshold voltage. There are three names. Okay, threshold voltage or cut-in voltage. Cut-in voltage. There are different names for this, and it is found to be for germanium. If the diode is made up of germanium, approximately it is 0.2 volts, and for silicon it is approximately 0.7 volts. Okay, for germanium it is 0.2 volt, and for silicon it is 0.7 volt. Now, when the diode is in the reverse bias, okay, and the so what happens, it will increase linearly. See here, as you are increase this voltage is said to be knee voltage. Okay, this one is said to be knee voltage, or threshold voltage or cut-in voltage. This particular voltage, it means the diode will go in the conduction mode, is said to be knee voltage or threshold voltage or cut-in voltage. And yeah, so it is different for two different types of diodes. Okay, so the voltage of around 1 volt. Okay, now, so suppose when in this case, suppose if you're applying in forward bias, if you're speaking about forward bias, if the voltage is equal to 1 volt, then current is found to be approximately 30 to 80 milliamps. This much current flows. Okay, 30 to 80 milliamps of current flows to the diode. Next one. Now we'll go to the reverse bias. Is it clear? Is this clear, sir? VI characteristic. Yes, Sayam. Sayam and Zayam.
Yes, sir.
Okay. So we will go to the reverse bias now. In reverse bias, what happens? This is for forward bias. This is for forward bias. Next is reverse bias. In reverse bias, what will happen now? In reverse bias, so here the junction current is very less. The junction current is, this will be asked in Viva. You know, this all this whatever I'm writing here. What is threshold voltage? What is what is reverse saturation current, leakage current? All these things will be, all these definitions will be asked in the Viva. So junction current is very less. Okay, very less in forward bias, in reverse bias. Below, very less below the breakdown voltage. Below the breakdown voltage. So what happens at the breakdown voltage? At breakdown voltage, at breakdown voltage, a breakdown voltage, the current increases rapidly. The current increases rapidly for a small increase in voltage. For a small increase in voltage. So offers low. So what happens in forward bias? It offers very less resistance. Offers very less. It offers low resistance. In forward bias, offers low resistance, and reverse bias high resistance. It offers high resistance. Offers high resistance. So that's the difference between both of them. The sharp increase in reverse current is due to sudden decrease in resistance. There is a sharp here. If you see the sharp here, when you look at this point, there is a sharp increase in the current. Yeah, see, current is for the same one, current is 40, 30, 50, it is increasing suddenly. So sharp increase in current, sharp increase in current is due to sudden decrease in resistance. Is due to sudden decrease in resistance. Sudden decrease in resistance. Clear? Any doubt in this? That is due to the sudden decrease in resistance. Okay? Is that clear? Yes. Is this clear, sir? Now, where do we use diodes? We'll study about the diodes and types of diodes. Okay, I'll just end with this one. Applications of diode. Diodes are used where in rectifiers. What are rectifiers? Rectifiers are the components which convert AC to DC, and it is also used to block the current flowing out of the batteries. We keep the diode in the reverse bias, and so that current will not flow. But there are many applications of diodes. Okay, there are many applications of diodes. Now we have different types of diodes. First of all, we need to discuss about Zener diode. Then there are three more diodes. That is LED, photodiode, and solar cell. These three we have to discuss. Okay. Tomorrow 10 o'clock I will take the class. Is that okay?
Yes,
Tomorrow
sir.
10 o'clock. So please, I have already written all the 3 days. I'm going to take from 10 o'clock, 10 to 11. Is that okay? The time is comfortable.
Yes, sir.
Okay. So tomorrow I will complete this part, and if possible, I will start with the Viva also, experiments and Viva. Okay. Okay, Zayan.